Okay, so let's pick up where we left off on the last video. The last video was just a review of first semester linear regression analysis concepts. And the problem was all about pharmaceutical companies and the number of research programs that they run concurrently and the average number of patents that are a result from each of those programs. And the data was produced a line of best fit of right here. Couple things of importance would be the slope. Okay. For each additional concurrent program, the mean number of patents resulting from that program is predicted to decrease by 0.11. So the slope analysis was always really important back in first semester, and it's still going to be the focus of the linear regression t-test. Now, something else that was of importance was the correlation coefficient. R equals negative 0.973, which we would term as being very strong negative. Now, something to note, this model was built from a sampling of 6 pharmaceutical companies. What if we had a model which investigated every pharmaceutical company and every set of concurrent research programs being conducted by those companies? Well, we would go from having a sampling model to having a population model. And that's what the linear regression t-test is all about. What if we were to build a population model? So, we know the notation for the sampling model. This was first semester. Now we get into the notation for the second semester. Y hat equals beta sub 0 plus beta sub 1x. And you can tell by the positioning what everything is. The A value is the same thing as beta sub 0, only this is the sample notation and that's the population notation. And then the beta sub 1 is the slope. Okay. There's the population notation and there's the sample notation. Okay. Now, conditions for the linear regression t-test. A couple of old familiar things from first semester. The data needs to be a random sample. We are supposed to check the scatter plot and make sure that the scatter plot is linear. We're supposed to check the residual line plot and make sure that it has no pattern in it. That would be an indication of independence. But now here comes the fourth condition. Here comes the new condition for testing the population model. The histogram of all the y values at each value of x is unimodal and symmetric, meaning it's approximately bell-shaped. Now, when we took the sample, every x value only had one y value. But thinking of it as a population, what you have to think about is what every y value would be if you examined every x value possible in the population. And what we see is the y values at every value of x are distributed in a unimodal and fairly symmetric pattern, okay, or a bell shape. And that's what gets us onto the t-curve. Remember, anytime you're on the t-curve, your data needs to be unimodal and approximately bell-shaped. So that's the condition that takes us from a sample model to a population model. The idea that every x has a distribution of y's that are unimodal and approximately symmetric. The sample we used only examines one of those y's within the distribution. All right, so let's do the actual test. Here was the data that we used in the last example. The number of concurrent research programs and the mean number of patents from each one of those programs. And I have that data in the calculator. There it is right there, X and Y. And if you go back and calculate the linear regression equation, stat calc lin reg a plus bx, there's the data, there's the line of best fit right there that we've got. Okay. Now, again, like I told you, it's going to be the slope that is of big importance right now, because it's the slope itself that directly connects the X and the Y variable, the mean number of patents with the number of research programs. So what we're doing is we are testing the significance of that slope. Is it a significant number or not? Because if it's a significant number, then the relationship between these two variables is also significant. So review, the null hypothesis is always a statement of insignificance. It's the alternative hypothesis which shows significance. So the null hypothesis would be that this number is an insignificant number. Now the symbol for slope in population form is beta sub 1. And the value of an insignificant number would be 0. So there's your null hypothesis right there. Beta sub 1 equals 0. Now, if it turns out that we fail to reject the null hypothesis, and that's an insignificant number, then it means whatever number it is, it might as well be 0. And if it's 0, then it means the relationship between these two variables basically doesn't exist, or at the very least, it's insignificant. It's an insignificant relationship. And if it's an insignificant relationship, then this variable might as well not be studied in the data. It's an insignificant variable. Now, let's move on to the HA, the alternative hypothesis. The alternative hypothesis is the slope is a significant number. So, beta sub 1 does not equal 0. The slope is significant. And if the slope proves to be significant, then it also means the relationship among these two variables, the independent variable and the dependent variable, is also a significant relationship. Now remember, we're going to be on the t-curve, and so we're doing a t-test, and anytime you're on a t-test, you need degrees of freedom. So technically speaking, the degrees of freedom equals the sample size minus the number of independent variables in the equation minus 1. But for our purposes, we are going to limit our analysis always to just one independent variable, like this right here. You can do analyses that have a lot of different independent variables within the equation at once, but we're limited to just doing one right now. So for all intents and purposes, the degrees of freedom is simply n minus 2, because it's n minus 1 minus 1 more. So the degrees of freedom is going to be n minus 2. So the next thing we have to do, we have to draw and label the curve. And remember, it's the t-curve. So the degrees of freedom are going to be the sample size, which is 6, minus the one independent variable that's in the equation, minus 1 more. So 6 minus 2, which is 4. And remember, it's a two-tailed test because it's equal to versus not equal to. So on the t-curve, at 0.05 with a two-tailed probability, the critical points are plus and minus 2.776. So there's rejection area up here. It's a two-tailed test. So my critical points are 2.776 and negative 2.776. Because remember, 0 is sitting right there in the middle. All right, now it's time to do the test. It's really simple. It's where all the other tests are. Stat, test, and then just go down to linear regression t-test. There it is. Okay. My X's are in list 1, my Y's are in list 2. I am doing a two-tailed test, so just say not equals to, and then drop down to calculate. Now, a couple things we're going to get out of it. The T star, the test statistic, negative 8.40. So T star equals negative 8.40. And we're also going to get the p-value of the test, which is 0.001. So we can make our conclusion. Using 95% confidence, there is evidence to, and if you base it on p-value, it's going to be a rejection. If you base it on the T star, because if this is negative 2.776 right here, then negative 8.40 is going to be somewhere over there in the rejection region. So any way you look at it, the conclusion is we have evidence to reject HO. Okay. Now remember what that means. Let's go back to the HO and the HA. We are now rejecting the HO. And this was the HO. Okay, beta sub 1 equals 0, which is an indication that the slope itself is an insignificant number. We're rejecting that. It doesn't equal 0. And so the slope is significant. So the slope appears to be significant, making the association between the number of research projects and the number of patents a relative relationship. So since we showed that number to be a significant number, then the relationship among those two variables is a relevant relationship.